Hello and good afternoon, everyone, and welcome to our event entitled Introduction to MPLS VPN. I'd like to start off today by explaining the format of the WebEx. This is a two-way interactive session, and you'll see the slides on the screen and hear live audio from our speakers. And during today's session, our phone lines will remain muted. To ask a question, please use the Q&A tab that's located on the right side of the screen. If you have any technical questions, please use the chat tab. Our facilitators will respond to those immediately. With that, I'd like to thank everyone for spending time with us today, and I'd like to pass it off to our presenter, Satish Chandran. Satish.
Thank you, Lindsay. Hello, and welcome to the Cisco Support Community. Today, we present a live Cisco Support Community Expert Series webcast. During our event today, our topic will be Introduction to MPLS VPN. My name is Satish Chandran, and I'm the Community Manager for Cisco Support Committee here at Cisco. Our expert joining me today is Nagendra Kumar, a Senior High-Touch Tech Support Engineer based in India and a double CCIE with broad experience supporting major service provider customers in routing and MPLS technologies. Welcome, Nagendra.
Hello, friends. Thanks, Satish. Now
I'd like to briefly outline the format for today's Expert Series webcast. Nagendra will start with a short presentation on Introduction to MPLS VPN for the first 25 minutes of the program, and then we will dive into the live question submissions for the remainder of the event. During our live presentation, you may submit a question to be answered by Nagendra and a team of Cisco technical experts using the Q&A panel, which is on the right-hand side of the console. The team of technical experts is well-versed in routing and MPLS technologies, so please begin posting your questions now to give us the best chance of answering them. If you experience any technical issues, please post your question in the chat window, which is again on the right-hand side of the window. We will be asking polling questions during this webcast, and we encourage you to participate by answering them. You may download a PDF copy of today's presentation using the link which is in the chat window. Now let's get started with today's event. Let's get started with the first polling question for the audience. What is your level of experience with MPLS VPN? A. I know basic MPLS, but no idea about MPLS VPN. B. I theoretically know MPLS VPN, but no practical experience. C. I'm playing with it in the lab. D. And I'm running it in the production. Please take a moment to answer, and this will give Nagendra an opportunity to tailor his presentation to your needs. And we'll display the results in a short while.
Just stand by for that. I'll get the polling question up in just 1 second. Please continue.
Thank you. So also make sure to submit your questions as we will be answering them later in the webcast. Now I'd like to hand over the mic to Nagendra, who will give you an expert look into the MPLS VPN solution. Over to you, Nagendra.
Thank you, Satish. Hello, friends. Thanks for joining this presentation. I'm Nagendra from Cisco HTTS team. So this is our agenda for today's presentation. We'll be discussing about Introduction to MPLS VPN. As part of introduction, we'll be discussing about MPLS VPN architecture, how does it function at control plane and data plane, followed by basic configuration and troubleshooting on MPLS VPN setup. So before starting with MPLS VPN, first, what is VPN? VPN is basically a group of sites or a collection of sites that are connected through common backbone network and are allowed to communicate among themselves based on certain policies. Though these sites are connected through common backbone network, these set of administrative policy will help us define which site is allowed to communicate to which other sites and thereby providing privacy between end customers, and that's VPN, Virtual Private Network. These policies not only define the permission to communicate between intersite, but also help us define how the traffic flow from one side to other side should be. Should it be any to any side connectivity, or in other words, should it be fully meshed, or should it be partial meshed, or even hub and spoke topology? So normally the policies will be defined by customers and can either be implemented by service provider or by customer. It basically depends on what VPN model we use. For example, if it is a IPsec VPN model, the policies like what is the hashing algorithm, what is the encryption mode, what is the peering address, so these policies will be defined by customer and will be implemented by customer on customer box. Wherein there are other VPN model where the policy will be defined by customer but will be implemented by service provider, and MPLS VPN is one such model. So the sites which are allowed to communicate among themselves, if they belong to same organization or enterprise, it can be thought as intranet VPN, and if they belong to different organization, it can be thought as extranet VPN. Even the VPN service customers can even span multiple service providers. There is no special requirement that all these sites should be connected to one common service provider. For example, assume service provider A is providing VPN service to customer A, and some of the branch sites of VPN A are in some branch remote location where it cannot be directly connected to service provider A POP but can be connected to service provider B POP. By having some business agreement between service provider A and service provider B, the VPN service can be provided seamlessly to all the sites of VPN customer, and this is inter-AS VPN service. So the VPN service can either be at layer 2 or layer 3. If it is a layer 2 VPN, the service provider devices doesn't get involved in routing. The routing relationship will be between customer sites. Best example would be frame relay or ATM, where virtual circuit will be pre-established between endpoints of customer side over which the data traffic will be flowing. And if it is a layer 3 VPN, the service provider devices get involved in routing and are responsible for advertising the prefix, the routing information from one site of a customer to other site of same customer. It got its own pros and cons. With layer 2 VPN, because the service provider devices doesn't get involved in routing, the amount of memory and the CPU processing cycle that is required to process all the routing information from all different customers are now saved. But the downside is that being layer 2 VPN, QoS is very hard to implement, as packet classification is nearly impossible at layer 2 level. And with layer 3 VPN, now, we don't need any pre-established virtual circuit between the end devices to have the data traffic flowing over. Rather, the routing will be taking care of it. And the downside is, now customers' network resiliency not only depends on customers' convergence time, but also depends on service provider network's convergence time. So in this presentation, we'll be discussing about MPLS VPN, which actually is a variant of layer 3 VPN. So before MPLS VPN, the layer 3 VPN was provided using tunneling concept. So the problem with tunneling scheme is that we soon end up with scalability problem. Assume one of your customer requests for a any-to-any site or fully meshed VPN service. We have to create a fully meshed tunneling scheme between all the endpoints of customer, and so soon we'll be hitting scalability problem. It's not only about scalability problem. Even per VPN or per customer QoS is very complex to implement. Moreover, the services, the managed services like shared internet gateway or shared VoIP gateway, these managed services should be moved out of service provider's network and can no longer be integrated with service provider's network. So while designing MPLS VPN architecture, some of these concerns are addressed. Yeah, so I think we got the polling answer. So the result is
most of the audience from basic MPLS and theoretical knowledge.
That's right. Yeah. Okay. So before jumping into MPLS VPN architecture, this diagram will give you a pictorial representation about what is intranet and what is extranet VPN. As you can see in this diagram, customer A is allowed to communicate with other site of customer A and also allowed to communicate with customer D. Similarly, customer B is allowed to communicate with other site of customer B and also with customer D, while customer C is allowed to communicate only with other site of customer C. So in this scenario, customer C is a pure intranet VPN customer, wherein customer A and customer B have both intranet as well as extranet VPN service. So this diagram will give you an overview about MPLS VPN architecture along with the terminologies that we'll be using in this presentation. So as everyone might be aware, the basic necessity for MPLS VPN service is that MPLS should be enabled on service provider core. Any router that performs packet forwarding based on label, or in other words, any router that performs label switching is known as LSR, label switch router. To start with CE device, customer edge, as the name says, is a device that will be sitting at the edge of the customer side, which will be connecting the customer side to provider network. And PE device, provider edge, again the name says, provider edge device is a label switch router that will be sitting at the edge of the provider network that will be connecting the customer side to MPLS backbone. The interface on PE device, which is connected to the CE device, is known as VRF interface. And provider LSR is again a label switch router that belongs to service provider without any customer side directly connected. So the basic functionality of provider device is to provide intercommunication between CE devices. So before starting with MPLS VPN service, even before start providing VPN service, the first and foremost thing we need is to have reachability between PE devices over LSP. So it's not plain IP reachability, rather the reachability between PE devices should be over LSP, label switch path. So to achieve this, we need to enable any routing protocol to propagate the PE routing information to other PE devices, and to enable MPLS LDP, label distribution protocol, or traffic engineering to establish end-to-end LSPs between PE devices. Now once this is done, the core is now ready to provide VPN service. As we saw earlier, for any VPN service, we need a set of policies. So the basic policy for a basic intranet VPN service is that traffic from one site of a customer should be delivered only to site of same customer and not to other customer. This is achieved by VRF, virtual routing and forwarding. VRF built its own routing and forwarding, the RIB and FIB table, and each VPN customer will belong to a separate VRF. So having said that, each VRF customers will be having their own routing table. We now have the privilege to use overlapping address between VPN customers for address conservation. Now the PE devices will propagate the reachability information of the VPN customers to other PE devices via BGP. Now that raises two questions. Question one is, BGP holding only one table, how does it differentiate the overlapping address from different VPN customers? And question two is, when any PE device on receiving the update from a remote PE device, how does it understand if there is any VRF interested in installing the prefix into? The answer for question 1 is RD, root distinguisher. Root distinguisher is a 64-bit value that will be attached to 32-bit VPN prefix to make it as 96-bit VPN v4 address. By making this RD value unique and attaching this unique RD value to the overlapping VPN address, we get a unique VPN v4 address of size 96-bit. So this will be installed in BGP table and thereby differentiating between overlapping address from different customers. And the answer for question 2 is root target is a BGP extended community that will be attached to the BGP update while propagating the routing information about VPN prefixes. So any PE device on receiving the BGP update can use the RT value to decide if there is any VRF interested in installing the prefix into. So we will be discussing more about the RD and RT in the forthcoming slides. So VRF, as said earlier, the virtual routing and forwarding which build its own RIB and FIB table, and each VPN customer belongs to one separate VRF. So now, because each VPN customer belongs to a different VRF and have their own routing table, the services like DHCP, NAT, or even routing protocol should be VRF aware. And a lot of development have been done on this front, and these services are now VRF aware. The interface on PE device, which is connected to the customer side, will be associated with the corresponding VRF. So show IP VRF interface will give you details about which interface is associated with which VRF. And show IP VRF will give you a basic detail about what is the associated RD value to a VRF and what are the list of interface that belongs to the VRF. So on any PE device, along with the VRF routing table, it also holds a global routing table on which all the other PE devices and the provider devices reachability information will be populated. So on a PE device, when you execute show IP root, the content that will be displayed is from global routing table. And if you want to display the content from a specific VRF's routing table, we need to use show IP root VRF and the VRF name. As you can see here, this is an example of VRF1's routing table. As you can see, there are a bunch of prefixes learned via BGP, one is connected and one is RIP learned. So this RIP is the VRF aware routing protocol running between PE and CE. For any BGP learned prefix which is received from remote PE devices, the next hop recursive lookup will be done on global table. For any other routing protocol learned prefix, the next hop recursive lookup, if required, will be done on local VRF's routing table. So VRF not only builds its own RIP table, but also builds its own FIB table, forwarding information base, which is our CEF table. So again, show IP CEF will display the content from global CEF table, and show IP CEF VRF and the VRF name will display the specific VRF's CEF table. RD, root distinguisher, is a 64-bit value that will be attached to the VPN prefixes of 32-bit to make it as 96-bit VPN v4 address. So the RD comprises of two subfields, administrator subfield and assign number subfield. As you can see in this example, there are two ways of representing RD. ASN:NN or IP address :NN. So when we use ASN:NN, it's type 0 RD, and when we use IP address :NN, it's type 1 RD. So these two types are two different ways of representing RD, and there is no functional difference between these two types. Still, it holds true that the basic functionality of RD is to make an overlapping address unique into BGP table. Route target is a BGP extended community that any remote PE devices on receiving the BGP update can use to identify if there is any VRF interested in installing the prefix. How does it operate? Any PE device, while generating the BGP update for the VPN prefix which is learned from the customer side, it will attach one or more root target value to the BGP update and will be propagating to remote PE devices. The remote PE device on receiving the update will pull the RT value, route target value, and scan through its VRF configuration to see if there is at least one VRF who is interested in importing the prefix into. And once it finds the match, it will remove the RD value and insert the 32-bit prefix into the corresponding VRF's routing table. So this example will give you this is an example of intranet VPN service with VRF, the RD and RT configuration. As you can see here, Site 1 and Site 2 of VPN A customer are connected to different PE devices, and the PE devices are configured with VRF A with RD value, root distinguisher value as 1:1 and root target both import and export as 1:1. Now, when any VPN prefix is learned from Site 1, the PE device will generate a BGP update and attach root target of value 1:1 based on configuration root target export 1:1. This BGP update will be propagated to remote PE device, and the remote PE device on receiving this update will pull the RT value of 1:1 and scan through its VRF configuration, and it can match VRF A as per configuration root target import 1:1. Now remote PE will remove the RD value, root distinguisher value, and install the 32-bit VPN prefix into VRF A's routing table. This is an example of extranet VPN. As you can see, VPN A and VPN B are different customers connected to different PE devices, and the PE devices are configured with VRF A RD value of 1:1 and root target import and export as 1:1. Similarly, for VRF-B, RD of value 1:2 and root target import and export as 1:2. Now with this configuration, prefixes from VPN-A will not be installed in VPN-B's routing table, and VPN-B prefixes will not be installed in VPN-A's routing table. Now for some business reason, VPN-A and VPN-B want to have extranet connectivity. How do we do that? Under VRF-B, simply import RT 1:1 and under VRF-A, import RT 1:2. By doing this, VPN-A prefixes will now be installed in VPN-B's routing table, and VPN-B prefixes will be installed in VPN-A's routing table, and thereby providing extranet connectivity between VPN-A and VPN-B customer.
Okay. Before we get back to the presentation, I'd like to take a moment to ask another polling question. The question is, how familiar are you with BGP? A. Theoretical knowledge only, and BGP is not running in the production network. B. I have minimal hands-on with BGP, but is not running in my production network. C. I have BGP running in my network and work on it on a daily basis. And D. I have BGP running in my network and I participate in IETF discussion for BGP-WG. Please submit your response now and we'll display the results a little bit later. Over to you, Nagendra. Thank you.
Thank you, Satish. So BGP plays a key role in MPLS VPN. All PE devices are required to have fully meshed BGP session with other PE devices. Alternately, we can also use root reflector concept, but the basic idea is that when any PE device, while sending a BGP update, it should be received by all other PE devices sharing the same service provider core network. Along this presentation, you would have noticed that the BGP update is not actually carrying IPv4 address, rather it is carrying 96-bit VPN v4 address. So even before sending and receiving the BGP update, the PE devices have to signal the capability, it has to negotiate the capability of sending and receiving the VPN v4 address with other PE devices. How do we do that? Under router BGP, we enable VPN v4 address family with other PE devices. Once this is done, the PE devices will be able to send and receive the VPN v4 updates. Now this BGP update not only carries VPN v4 and RT, but also carries MPLS label that is allotted by PE device for each and every VPN prefix received from customer side. Why do we need this MPLS label? On a PE device, when a packet is received from customer side, based on the incoming interface's associated VRF, the local PE can understand, okay, this packet belongs to this VRF. But if a packet is received from remote PE, the incoming interface will be core-facing interface, core-facing MPLS interface. And so, which is the core-facing interface will be in global routing table, and so the local PE may not be able to understand which VRF does this packet destinated to. Assume a packet with destination 10.1.1.1 is received on the core-facing interface, and if we have 10.1.1.1 in both VPN A and VPN B's routing table, the local PE may not be able to understand if this packet is destinated to VPN A or VPN B. This MPLS label helps us here. How does it help? The PE device, while propagating VPN A's 10.1.1.1, will allot a label of say 100 and will be propagating the BGP update to remote PE devices. Similarly, for VPN B's 10.1.1.1, a label of 200 will be allotted and will be propagated to remote PE devices. So when a packet is received with the label of 100, the local PE can understand, okay, this packet is destinated to VPN A's 10.1.1.1, and if a packet is received with the label of 200, it can understand, okay, this packet is destinated to VPN B's 10.1.1.1. So just got the BGP polling answer as well. So I think we have a good number of people running BGP in network. Okay, so the label which we discussed in the previous slide, is known as VPN label. I mean the label which we received via BGP from different PE devices. So as you can see in this presentation, or even you would have noticed in our previous discussion, the BGP update will be propagated only between the PE devices, and the intermittent device don't have any knowledge about the customer, the end VPN customer's prefixes. So now when any PE device, if it only to use the VPN label which is received via BGP, the intermittent provider devices, because they don't have any knowledge about the customer prefixes, and so the VPN label may end up dropping the packet. So what do? Now we not only push the VPN label, but also push one more label on top of it to deliver the packet to remote PE device. So along the path, this label will actually be learned via LDP. So the intermittent provider devices will be looking into the top label and will deliver the packet to the remote PE, and remote PE will actually look into the VPN label and will send it across to the desired CE devices. So on control plane, how does the routing exchange happens between CE devices? The CE device will advertise the VPN prefix to PE device, and PE device being running VRF aware routing protocol with CE, it can understand, okay, this prefix belongs to this VRF and will populate the right VRF routing table. Now, this routing table being redistributed into BGP, the local PE will generate a BGP update. Attach the RD value of the VRF to the VPN prefix to make it as VPN v4 address. Attach the required RT value, root target value, and allot a label, VPN label, and propagate the BGP update to remote PE devices. The remote PE device on receiving this update will pull the root target value and scan through its VRF configuration, and once it finds a matching VRF, it removes the RD value and install the VPN prefix into the corresponding VRF routing table, and install the VPN label into the VRF's corresponding FIP table, and will advertise it to remote CE. Now once the route exchange is done between the CE devices, how does the packet forwarding happens at data plane? The CE device will be sending a plain IPv4 packet to the PE device. The PE device, based on the incoming interface associated VRF, will be performing a lookup into the corresponding VRF's forwarding information base table and push two labels. The bottom label is the VPN label, which is received via BGP for this prefix from remote PE device, and the top label is the IGP label learned via LDP to reach the remote PE device. Along the path, along the core, the provider devices, the intermittent provider devices, will be performing a MPLS label action of label swapping on the top label, and the bottom label, the VPN label, will not be disturbed. Once the packet reaches the provider device, which is directly connected to the remote PE, the default action is to pop the top label and will be sending with VPN label intact. The remote PE, on receiving the packet with VPN label, will use this VPN label and perform a lookup into its LFIB, label forwarding information base table, to identify which VRF does this packet belongs to, and will be sending it to the desired CE device. So this slide is to reiterate the control plane basics on MPLS VPN. Assume CE3 and CE4 belongs to VRF blue, and CE1 and CE2 belongs to VRF yellow. So from control plane's perspective, on PE device, we just configure two VRF so that each VRF will be in a different routing table, VRF blue and VRF yellow, and will be using BGP to propagate the VPN reachability information between PE devices. So these are few of the elements that helps us to separate the control plane information from different customers. To start with, VRF. VRF asset will be building its own routing and forwarding table, and so totally segregating the control plane information from one customer to other customer. And when it comes in terms of BGP, RD comes into picture and will be attached to the VPN prefix to make it unique in BGP table. Now the VPN v4 signaling capability of BGP helps us send a BGP VPN v4 address to remote PE devices. So this is again to reiterate how the packet forwarding happens on the data plane. So the PE device, based on the incoming interface associate VRF, will be looking into the corresponding table and will be pushing two labels. Bottom is VPN label and the top label is IGP label. Along the path, the label swapping will be happening on the top label, and remote PE device, once it receives, will use the VPN label to identify which VRF the CE device belongs to and will be sending across to the right CE device. By now, I think you will have a basic understanding about MPLS VPN architecture and how does it function at control plane and data plane. So this is a basic configuration for MPLS VPN. On CE device or provider device, we don't need any special configuration or extra configuration. The only requirement is that on provider device, MPLS should be enabled. So we only need extra configuration on PE devices. So this is an example from a PE device. As you can see, we start with defining the VRF using IP VRF and the VRF name. In this case, it's VRF1. Associate a unique RD value to this VRF 1:1 and configure at least one statement of root target import and root target export. Now associate the VRF on the PE device which is connected to the customer side to the corresponding VRF. How do we do that? Under router mode, under interface mode, configure IP VRF forwarding and the VRF name. Now configure any VRF aware routing protocol between the PE and the CE device. In this case, we are using router OSPF, the process ID, VRF and the VRF name, and populate all the required networks there. While configuring BGP, we need to take care of two things. One is to enable VPN v4 signaling capability. How do we do that? Under router BGP, go to address family VPN v4 and activate all the required neighbors, either all the PE devices or the root reflector in case of RR environment. And the second one is to redistribute the VRF aware routing protocol into BGP. How do we do that? Again, enter router BGP, address family IPv4 VRF name, redistribute the routing protocol under that. So in this case, address family IPv4 VRF1 and we have redistributed OSPF 100. So show IP BGP VPN v4 all will display all the VPN v4 address in the BGP table. As you can see here, root distinguisher 1:1 followed by a set of prefix. All these are VPN v4 address in BGP table. So we saw that for MPLS VPN service, one of the basic requirement is to have LSP between PE devices intact. If we have LSP broken along the path, the intermittent provider devices may end up looking into the IP address of the packet, which actually will be destinated to VPN customer, and because the intermittent provider don't have any knowledge about it, may end up dropping the packet. So as part of troubleshooting, we need some way to identify if the LSP is broken or not. This is one way using traceroute. So traceroute is enhanced in a way to not only let us know the path address details, but also to give us the label information, the label details that will be used along the path. How does it work? I think everyone might be aware. Traceroute predominantly depends on two ICMP error message, the time to live expired error message and port unreachable error message. So these two error messages are enhanced in a way to carry the label stack. So when any router, while it was about to drop a MPLS packet for the reason of TTL expired, it pulled this label stack from the packet, drop the packet, generate ICMP error message TTL, and put the label details into it and send across to the ultimate source. So in this traceroute output, if you see an intermittent label missing, it says that the LSP is broken and we will be taking the required course of action. So these are the PEC routing protocol. Currently, IBGP is not supported in iOS. So with MPLS VPN, the troubleshooting tool and the management tool are also made VRF aware. So from a PE device, when we want to use ping or traceroute, it should be VRF aware, and ping VRF, the VRF name followed by the address, will perform a lookup into the corresponding VRF's routing table and will be sending the ping traffic. And same holds true for traceroute as well. And from a PE device, if you want to telnet into a connected CE device, we use telnet, the address followed by /VRF and the VRF name. So using this command, the lookup will be done on the VRF's routing table to pull the routing information and will be sending the packets. So whenever we have some connectivity issues between customer sides, we start our troubleshooting always with sending a ping traffic between the connected CE devices to see if we have the reachability. And if we have any problem, we try to narrow down the segment where is it getting dropped by sending or pinging from CE to the directly connected PE, and from PE to remote PE, and from remote PE to the connected CE. And once we identify the segment, we'll be looking into a respective table to identify if there is any control plane information missing that is resulting in this problem. So in this presentation, we'll be logging into a live setup to quickly have a look into what are the troubleshooting tools that can be used on CE and PE, and the different tables, what details, what control plane details to look into those tables. So this is the setup we will be using. CE1 is connected to PE1, to provider, to PE2, and to CE2. So from CE device, the troubleshooting tool is as normal. The ping and trace route we use as usual in any other devices. So from PE device, if I want to check the reachability to other from CE device, if I want to check the reachability to other CE device, I use ping to any address. So in this case, from CE1, I'm trying to send ping traffic to 11.100.1.5, which is the loopback address of CE2. And the other tool we can use is traceroute. So as you can see here in the output, traceroute output, it not only gives the path address detail, but also gives the label information that will be used along the path. This will help us identify if there is any broken LSP. As said, on PE device, we now want to use VRF aware troubleshooting tools. So from a PE device, if I want to reach any VRF customer's address, in this case, if I want to send a ping traffic to CE2's 11.100.1.5, I should use VRF aware ping. So in this case, the VRF name is VRF1. As you can see here, VRF1 is associated with RDF1:1. So if I want to use troubleshooting tool ping VRF1 11.100.1.5. Same is for traceroute. As said, it not only gives the path address but also gives the label details. Now, if we have any problem in the connectivity, what are the control plane details, or what are the tables and the details we will be looking into? On CE device, we don't have any special configuration, and so if we have Ceph enabled, we will be looking into the Ceph table or into the routing table to make sure it is pointing towards the right next hop and right outgoing interface. In this case, I'm checking the Ceph entry for 11.100.1.5, which is the loopback address of CE2. As you can see, this is pointing towards 11.1.1.2, which is PE1 address, and the outgoing interface is serial 2/0. So CE1 will be sending a plain IPv4 packet destined to 11.100.1.5 to PE1 device. The PE1 device, based on the incoming interface associate VRF, will be looking into the corresponding VRF's FIP table to pull the label details. So in this case, the incoming interface is serial 2/0, which is associated to VRF1. So we'll be looking into VRF1's FIP table, and you can see two labels, label 17 and label 20 are pushed. So label 20 is the VPN label or the bottom label, and label 17 is the IGP label or the top label. Now, how do we make sure if 20 is the VPN label that we received via BGP from PE2? By looking into VPN v4 BGP table. Show IP BGP VPN v4 all 11.100.1.5. So you can see this is the VPN v4 address RD 1:1 with VPN prefix makes it as VPN v4 address, and this is the next hop 10.100.1.4, which is PE2. This is received with RT of value 1:1, and this is the VPN label 20. Now fine, VPN label is 20, that's the right label which we received via BGP. Now how do we make sure if 17 is the label, IGP label, to reach PE2? As we said earlier, for any BGP learned prefix, BGP learned update from other remote PE devices, the next hop recursive lookup will be done on global table. So the global table, the global recursive lookup on CEF table for 10.100.1.4 will give you the IGP details. So the IGP label is 17. Now PE1 will be sending the packet with bottom label as 20 and top label as 17 to provider device. The provider device on receiving it will perform a normal LFIB lookup for the top label, which is label 17. As you can see here, the action is to pop the label and send it to PE2. Now PE2 will be receiving the MPLS packet with a label of 20. The remote PE device again will be looking into its LFIB label forwarding information base for label 20 to identify which VRF does this belongs to. As you can see here, for label 20, the action is to remove the label, and this is actually destinated to 11.100.1.5 and it belongs to a VRF. Now how do I check which VRF does this belongs to? The detail will give you the details about the VRF. It belongs to VRF1 and the outgoing interface is serial 2/0. Now PE2 will be removing all the labels and will be sending a plain IPv4 packet to CE2. So as part of troubleshooting, these are few of the debugs that will help to get more details about the control plane information. So again, on CE device, we don't have any special configuration, and so we simply rely on debug IP routing. On PE device, we can use two debugs. One is related to BGP, debug IP BGP VPN v4 unicast update. That will be giving more details about the BGP VPN v4 BGP updates sent and received. And VRF aware routing, debug IP routing, VRF and the VRF name. So MPLS VPN is one of the service that can leverage the existing MPLS infrastructure. So there are other services that can also leverage the existing MPLS infrastructure like ATOM, any transport over MPLS, MPLS QoS, or even traffic engineering. So this diagram will give you a basic idea about all these services that can be running on MPLS infrastructure.
Thank you, Nagendra. So let's move on to the polling question 3. What advanced MPLS topic are you interested in future? A. MPLS traffic engineering. B. Layer 2 VPN. C. Multicast over MPLS, that is MVPN. And D. MPLS QoS. Please take a moment to answer. Thank you, Nagendra. Great presentation. Also, thank you everyone for participating in this event polling. Let's see the results of the... Now it's time to answer some of the questions our viewers have submitted in the Q&A panel. By the way, if you can't stay for the Q&A, please be sure to click on the evaluation link provided in the chat to let us know how the session met your business needs and expectation. The first 5 listeners to complete the evaluation survey will receive a $20 gift card. To complete the evaluation, please click on the link provided in the chat window. Now let's get started with the Q&A. The first question to you, Nagendra. How is MPLS VPN different, or is it similar to generalized MPLS or GMPLS?
Okay, GMPLS is more about layer 1. It's like MPLS on layer 1, wherein MPLS VPN is a layer 3 VPN.
Okay, thank you. So let's move on to the next question. How does MPLS VPN support IPv6, or is it support IPv6? Does it support?
Okay, so I'll rephrase the question. Whoever asked the question, is it like the VPN customers or IPv4, or can it be supported IPv6? In that case, my answer would be yes, it supports. With 6PE and 6VPE, the VPN customers can run IPv6, and the VPN IPv6 prefixes can be exchanged over BGP, and still, because the core is running labeled LSPs, it doesn't look into the layer 3 information. Rather, the intermittent provider devices will just look into the label information and can still pass through the IPv6 packet from one customer side to other customer side. So if the question is, does it support IPv6 as VPN customer? Yes, it supports.
Okay, thank you. I see next question. If running an IGP like OSPF on the PCE interface, does the CE need to run BGP at all?
Not required. So when you run OSPF as your PCE on PE device, obviously you need to enable OSPF on the CE side, and you don't need any BGP. But we can also use eBGP as PCE protocol.
Okay. The next question is, can we use multicast over MPLS network?
Okay, so as far as multicast is concerned, recently they have introduced a concept called LSM. So earlier it was not, the multicast package will not be label switched. Rather, we need to enable multicast on core also. So the multicast packet from the VPN customers will be encapsulated using GRE, and it will be having a destination address of one more multicast address, which actually is enabled and running on your core interface. So recently they have introduced a concept called label switched multicast, which uses P2MP traffic engineering or multicast LDP, multi-point LDP, that can provide a label switched multicast packets.
Okay. Thank you. And the results are out for the polling question 3. And I think 27% of users says for the first, that is MPLS traffic engineering, as the next topic of webcast. Why does the last hop in the trace? I think this is this relates to the presentation or the desktop that you have shared. So I'll skip this, and Nagendra will answer this question later when we create the discussion. Moving on to the next question. How LSR choose which label to use if there are 2 labels for the same prefix, 10.1.1.0/24 and 10.1.10/32? I think this is also related to the presentation. So, Nagendra, would you like to answer it later?
Yeah, if you can repeat the question.
Okay, that is, it says how LSR choose which label to use if there are 2 labels for the same prefix.
Okay.
And the address are 10.1.1.0/24 and 10.1.10, I think one subnet is missing, /32.
Okay,
So that's the
so
question.
it basically depends on, it's like normal routing. So where do you pull the label details from your Ceph table, and from your Ceph table, the best path will be selected based on your the subnet mask. When you have a /32 entry and a /24 entry, the more prefix or the more specific prefix will be chosen, and the label associated with that will be used.
Okay, thank you. And the next question is, how would you recommend monitoring MPLS VPN for performance, especially using NetFlow?
I need to get back on this because as far as monitoring is concerned, we need to discuss internally. So I need to get back on this.
Okay. The next question is, Layer 2 VPN can also be Ethernet. VPLS, I think that's the question. So I think it seems like an incomplete question. So I'll move on to the next one. On slide 34, you have neighbor on both IPv4 and VPN v4. Why? This is related to slide 34. Nagendra.
Slide 34. Yeah, so what is the question?
How neighbor on both, you have neighbor on both on this slide, IPv4 and VPN v4. Why?
Okay, so when you configure router BGP, by default, it will activate the BGP session for IPv4 with all the neighbors. There is of course ways to disable it, but by default IPv4 address family will be negotiated. For any other address families like IPv4 multicast or MDT, or in this case VPN v4, we explicitly need to activate all the required neighbors. So that's why as soon as you configure, normally when you configure router BGP and a neighbor, the remote AS and other details, and without any other address family, the neighbors will not be moved to address families. But the moment when you activate for VPN v4 or even for any other address families, these neighbors will also be moved to IPv4 address family. So that's an expected behavior.
Okay, thank you. And moving on to next question. On traceroute, what does the numeric key do?
Okay, so by default, when you execute traceroute, it just wait for the DNS resolution. Normally, in the service providers or even the actual production network, just for the sake of simplicity, they have DNS implemented, and when you execute traceroute, instead of giving you the address details, it just convert it into the host name of the device and will be displaying. So that will take a little bit of time to convert, to perform the DNS resolution and other stuff. Rather, if you use numeric, it won't wait for that resolution and just plainly give you the IP address details. So that will be more faster while comparing to a normal traceroute.
Okay, thank you. The next question is, can you tell me why there is no checksum field in MPLS header and why there is TTL field in MPLS header?
Okay, for checksum, intermittently we are not going to do any CRC checking, and that will be given to the layer 3 because MPLS comes in between like MPLS layer 2 and layer 3. It's like shim header, and so we don't do any CRC checking there because it's done in layer 2 as well as in layer 3. And regarding TTL, this is basically to avoid any looping that's happening or end looping happening on the MPLS network. So it happens like any other IP packet. Whenever a MPLS packet is forwarded, the TTL will keep decrementing, and the moment when it reaches 0, the packet will be dropped and will be sent a TTL expired error message.
Okay, thank you, Nagendra. And we are close to the time, so those questions which we could not answer here, Nagendra will be hosting an Ask the Expert event, which will start today. That is August 17 until August 26. So Nagendra will be answering all these questions which are posted today, and you are welcome to ask questions whichever you have in that Ask the Expert discussion forum. And you can log on to Cisco Support Community and go to the Ask the Expert tab at the top. So there you can find this latest discussion thread. If you haven't explored the Cisco support community yet, take a moment to check out the excellence within and the link is supportforums.cisco.com. And we'd like to inform you about our first Spanish webcast with Cisco Security CCIE and certified ethical hacker from EC Council, Ivan from HTTS Group in Latin America. The topic he'll be covering is Firewall Service Module Architecture and Operation. This will take place on August 30th at the time mentioned in the slide. The registration link will be posted in the chat so you can register if you speak Spanish. And the next, that is the English Expert Series webcast, we invite you to attend. And the presenter is a double CCI technical leader, Jazif Frahim. He's based in RTP. The topic will be Things I Do to Protect My Network from Getting Hacked. And this will take place on September 13th, 8 a.m. Pacific Time. You can register for the live webcast at www.ciscolive.com/ATE. And if you speak Polish, Japanese, or Spanish, we invite you to ask your questions and collaborate in your language. We are also running a pilot for Russian and Portuguese, and you can register at the following links mentioned in the slide. So before signing off, please take a few moments to complete your evaluation for today's session. This will help us address your business needs and interests in the future. Thank you very much, Nagendra, and the panelists Saurabh, Raju, and Anand for sharing your expertise with us today. Thank you and have a great day.
Thank you.